Today we're looking at the second fundamental theorem of calculus and the mean value theorem. So in regards to an integral. So the first one is that the mean value theorem states that if the function is continuous on a closed interval, then there exists a number c in the closed interval of a and b, see, number c, in the closed interval a and b, such that f of c times the change in x, so b minus a, is equal to the integral of the area under the curve from a to b. Okay, so in other words, at some height between the a and the b value, we can draw a rectangle with that height and the change in x that would have the same height, that would have the same area as the area under the curve. So in other words, the area of the rectangle is equal to the area under the curve. Okay, so we can rearrange this. Basically, the mean value theorem just says that there is some height that exists between the two values. So this height exists within our interval. That's it. So what we're going to do is we're going to use our mean value theorem to figure out our average value. So the average between A and B. Okay, so it's the average height of the rectangle, basically. No, it is the height of the rectangle. So f of c is equal to, I just multiplied both sides. Actually, I'm going to, multiply both sides by 1 over b minus a. And I get f of c, which is the height of that average rectangle, is equal to 1 over b minus a times the integral from a to b of f of x dx. So the area under the curve divided by all of the x values, the change in x. Okay. So here's an example. We're going to look at the average value of f of x is equal to 3x squared minus 2x, and on the interval 1 to 4. So we need to get the area under the curve, which would be from 1 to 4 of 3x squared minus 2x dx. And then we're going to take that area and average it out over all the x values. So I'm going to average it from the change 1 over the change in x. So 4 minus 1. I get 1/3 times, I'm going to integrate x cubed. So 3 over 3 will give me 1 minus 2x squared over 2 from 1 to 4. So you get 1/3 times x cubed minus x squared evaluated from 1 to 4. Okay, so I have 1/3 times 4 cubed minus 4 squared, and then minus the second, using our second bound, 1 cubed minus 1 squared. Okay, and make sure we're subtracting all of the second equation, so we need to put it in parentheses. Okay, so I get 1/3 times 64 minus 16, and then this is minus 1 minus 1 has 0. Woohoo! So 1/3 of 64 minus 16 is just, I believe, 1/3 of 48, which is 16. Okay, next, my friends, we have the second fundamental theorem of calculus. Okay, The second fundamental theorem of calculus just says that a function, if a function is continuous, then it will have an antiderivative. That's it. Okay, it might be one weird, complicated antiderivative, but it exists. So if the function is continuous, it has an antiderivative. So we have a function that is continuous on an interval, and so what we know is that this is cray, but the derivative of the integral of f of, from a to x of f of t dt is equal to f of x. And then if we, so it's like the derivative of the antiderivative is itself, basically, okay? So if we are upper bound, or one of our bounds is a function, we just have to apply the chain rule. So the second fundamental theorem of calculus says that the derivative of the antiderivative of from a to g of x of f of t dt is f of g of x, that's our inner bound, times the derivative of that inner bound. Okay. So I don't know what happened to our, I don't know. Okay, show the second fundamental theorem of calculus works by using a definite integral. So I'm just gonna show you, oh, I didn't change this one. I changed it on my paper. Okay, this is, we're not gonna take the square root. It's just 5t, okay? So what we need to do is start with the integral. So we're gonna do d dx of 5t squared over 2 evaluated from a to x. Okay, now I plug in d dx of 5x squared over 2 minus 5 times a squared over 2. Okay, and then we're going to take the derivative of that. Now the derivative of 5x squared over 2 is, bring down the 2, so we get 5x, reduce the power, and then remember a is a constant. What's the derivative of a constant? It's 0. So I see that the derivative of the integral from a to x of 5t dt is just 5x. It's the inside function with the t replaced with the upper bound. Whoa. Okay, so what the shortcut, again, I forgot to erase that. Okay, d dx of a of the integral from a to x of 5t dt is like, oh, the integral and the derivative are going to delete themselves, but I need to make sure that I plug in that x, so 5x. Okay, check out these weird integrals that we don't know how to solve yet because it's chain rule business. So I see that I have a constant and a function x, and then I'm taking the derivative of the antiderivative. So all I'm going to do, I recognize that as the second fundamental theorem of calculus. I take my function, and instead of t, I plug in x squared minus 1. And we technically have to take the derivative of x, which is just 1. So we're timesing by 1. So we just stop. That's it. Okay, next up, find the slope of we're going to find the slope of the integral of from pi over 2 to x cubed of cosine t squared dt. So I'm looking to see if anything is a constant. Constant. Whoop, whoop. And this is a function. Okay. If I'm taking the slope of this function, I'm going to find the derivative d dx of the integral of pi over 2 x cubed times the cosine of t squared dt. I recognize the second fundamental theorem of calculus, and I'm like, all I need to do is rewrite my inside function. So, but instead of t, I'm going to write x cubed, and then that is being squared. And then because the inside was not just plain x, I need to take the derivative, so times 3x squared. Rewrite 3x squared times the cosine of x to the 6th power. Done. Next, we're going to take the derivative of the integral from sine x to 2 of cosine t plus 2 dt. I'm not super keen on the function being on the bottom, so I'm going to write this as d dx, and I'm going to pull out the negative of from 2 to sine x, so I can flip the bounds of cosine t plus 2 dt. And I'm going to put the parentheses around the t, so I remember that the 2 isn't part of the argument. All right, time to take the integral, the derivative of the integral. So all I get is negative times cosine of, instead of t, I get sine of x times, or plus 2, okay? And then the derivative of sine x is cosine x. All right, the last one. We are going to find the value of each one of these parts. So we're going to find the value of g of x. Right now I have the function f of x over here. If I want to find the value of g of x, what I need to do is say, or g of 0, I need to find the area from 0 to 0 of f of t dt. And I know if the bounds are the same, the area is going to be 0. That's it. Let's do another one. Okay, so we have g of -1. We're going to evaluate from 0 to -1 of f of t dt. Okay, so I am going to say that g of -1 is equal to, from 0 to -1, the area 1/2 base times height gives me an area of 1, but I'm moving from right to left, so the area is going to be -1. Done. All right, number 3, g of 2. We're going to start with 0 and move to x equals 2 of f of t dt. So our g of 2 is from 0 to 2, the area under the curve is a circle. It's a quarter of a circle. So 1/4 pi r squared, the radius is 2, so 2 squared. So that gives me an area of pi. Okay, lastly, we have g of 5. So I'm going to start with 0. Okay. To x is to 5 of f of t dt. So from 0 to 5, I now need to get the area under this curve, or above this curve, which is, this triangle is a -1, and then this is a trapezoid. So I'm going to add, a trapezoid. 2 plus 1 divided by 2 times the height, or the base, which is 2. So 3 over 2 times 2 gives us an area of 3. So I just need to add the integral from 0 to 2 of f of t dt plus the integral from 2 to 5 of 2 to 5 of f of t dt. Okay, so I have pi minus 1 minus 3 gives us 4. So pi minus 4 is the area. All right, the last thing we need is just evaluating the graph. We want to find the points of inflection. So we have the graph of f of x, basically. And so where are the points of inflection? What I know is that if I took the derivative of, actually, let's just start with our given. So g of x is equal to the integral from 0 to x of f of t dt. Okay. If I take the derivative of each of these, g prime of x is equal to the derivative of the integral of f of t dt, right? Okay. So that means that g prime of x is equal to, remember, this is the second fundamental theorem of calculus. It says that if I take the derivative of the integral, then I just have the inside function with my x value as my input. So g prime of x is equal to f of x. So g double prime of x is equal to f prime of x. So in other words, I'm going to call this f of x, but it's also can be called g prime of x. They are equivalent. So the point of inflection would be when g prime of x has a change in the slope or a 0, a horizontal tangent line. Okay, so the point of inflection will occur when the slope of f of x changes signs. Fun times. So that occurs at x is equal to 0 right here. And x is equal to 3, 1, 2, 3. So the slope is negative and then it changes to positive. Okay. So we'll have points of inflections at 0 and 3.